All right. So let's begin by asking, do you guys have a question or clarification so far regarding with our discussions last meeting? Anyone?
None, sir.
All right. So if none, just give me thumbs up just to let me know that everything is good. All right. Okay then. So how many? Like 7 out of 8. What about you, Miss Maxine? So I think she's not around. Anyway, so let us start now with the module 6. So this is only a 22 slide module, so this won't take long. All right. So we have already talked Zener diode many times in our previous meetings before, but this is now the proper or the right time to talk about the Zener diode. Okay. So you guys already know the definition of a Zener diode. So this one works the same if it's a in a forward bias. Okay, so it behaves the same with a normal diode. However, in this one, the special thing about the Zener diode is this one starts to conduct in the reverse direction once it reaches the so-called Zener voltage. Okay, so you can say that this is the breakdown voltage of this Zener diode or this kind of diode. Okay, so we also call this one avalanche breakdown. Okay, once it exceeds this Zener voltage. All right. So in other words, it is especially designed to reverse breakdown voltage, which takes advantage of any reverse voltage applied to it. Okay. So if you guys are going to take a look on this one, so this one is the same with how the other diode works. Okay, so it doesn't conduct if it's in a reverse bias, and if it's non-ideal, of course, it will consume a certain amount of voltage, which is the voltage threshold before it will permit the flow of current. Okay, and then in reverse bias connection, so it will only permit the current once the rated voltage or designer voltage was reached. All right. So we have here a sample. Okay, so you could say that this is the circuit of a Zener diode. So yeah, it's like a diode also. However, in reality, we won't be able to see if it's if it's this one is a Zener diode or what. So maybe it just had a code wherein saying that that code is a Zener diode. So yeah, it's the same as the other diode. So we have a 150 volts of voltage source. We have a resistor, and then a diode. Okay, so in here, this will only start conduct once it reaches this rated voltage, which is 100 volts, okay, or at least equal to 100 volts. Okay, and then it will start permitting a current. But to differentiate, a normal diode into a Zener diode, so we do have this symbol, okay, or yeah, symbol icon for a Zener diode. So there is an additional wherein it has a line right here and then another line right here. So if you guys will see this one is a Zener diode, and this one is just normal diode. All right. So unfortunately, when normal rectifying diodes break down, they usually do so destructively. So it can blow up maybe, or it can destroy the entire circuit. Okay, so that's what it meant by destructively. So however, it is possible to build a special type of diode that can handle breakdown without failing completely. So this type of diode is called a Zener diode, wherein once it reaches that breakdown voltage, it won't uh, you know uh, get destroyed, or it won't get blew up. Okay. Instead, it will work as a forward bias, but once it reaches only this rated voltage. All right, so in reverse bias mode, they do not conduct until applied voltage reaches or exceeds the so-called Zener voltage. So are we clear so far with the definition or the description of a Zener diode?
Yes, sir.
All right. Okay, so if ever that you have a question, so just let me know. All right, so let's have an example then. So example number one, Zener diode. So find the V outs and total currents during the positive and negative half cycle of the circuit. So consider the diode as an ideal Zener diode. So there is no voltage threshold. So in here, this is a Zener diode. So as you can see, even though without this name, we already know that this is a Zener diode because of its icon. Okay, so it has a detailed line like this, which indicates that this is a Zener diode. And then we have a rated voltage of 5 volts. Okay, so this is not a voltage threshold, but this is a rated voltage that we need to reach if we are in reverse bias connection. So we have a voltage source of 3 volts, we have uh, a resistance of 1K, and then we're going to find the V outs and total currents of the positive and negative half cycle. So here is the solution during the positive half cycle. So during the positive half cycle, so we have positive to negative, negative to positive. So we have a reverse bias connection. Now, one thing that we need to check is, of course, if do we have enough voltage source to make, to make or to let us, let's say, break this rated voltage. Okay. So do we have that one? Is 3 greater than 5?
No.
Okay, so obviously no,
So
so this will stay as a reverse bias connection. So meaning there is no current that will flow on this diode. So that is why we have a V out of 0 and then we have a 0 milliampere for the current. Okay, so you can just make this one as open circuit. Okay, and then for the negative of cycles, so negative to negative and then positive to positive. So we now have a forward bias connection. So thus we now have a uh, V out, which is of course negative 3 volts, and then we have a current of negative 3 milliamps. So just use Ohm's law in solving the total current. So are we clear so far?
yes, sir.
All right, then. So just again, just let me know if you guys have a question. Let's now proceed to example number 2. So everything is the same. So we have to find the V out and then the total current. And we now have a different value of voltage source. So we now have 14 volts, and then we still have the same rated voltage of Zener diode, and then same resistance value. So for the positive half cycle, so we are in a reverse bias connection. So in here, 14 is now greater than 5 volts. So we have exceeded the rated voltage, okay, of this Zener diode. So thus, it will now permit a current on this diode. But in doing that one, okay, so this one now is like a closed circuit, right? So just make this one as a voltage source. Okay, so we have here negative and then positive. And if you guys are going to take a look at this one, they have a same polarity. Okay, negative and then positive right here. So basically, they will be added with each other, right? So 14 plus 5 is equal to 19. But that is not how it will happen. So if this one is in a reverse bias connection, you always need to deduct the rated voltage of the Zener diode to our voltage source. So that is why we have 14 minus 5 is equal to 9 volts. Okay, so in here, it's like a voltage threshold that we need to pass through. Okay, however, it's in a reverse bias connection. And at the same time, that rated voltage will be deducted into our voltage source. So that is why we have 9 volts only. And then for the current, so Z use Ohm's law, and then it will give us a result of 9 milliamps. And then for the negative half cycle, so everything is the same. So it's like a normal diode now. So we are now in a forward bias connection. So positive to positive, negative to negative. So we have a V out of negative 14 volts during the negative half cycle. And then we have a negative 14 milliamps for this current right here, okay, or the current of the entire circuit. So are we clear so far? Okay, again, yes, most of my students got this one incorrect. So yes, this is like a voltage source, but it's the other way around. So instead of adding, you need to deduct the Zener diode rated voltage. All right, so let's now proceed to example number 3. So we have to find the V out and the total current. So question, what is the V out or the V out value during the positive half cycle? Okay, just wait a second, guys. So just read this one and then just try to analyze what is the value of V out. Any guess?
20, sir.
All right. Yeah, that's correct for the positive half cycle. How about a negative half cycle? Anyone? What is our value of, what is the value of our V out during the negative half cycle?
Sir, negative 30.
Negative 30? Is it 30 or 20, Mr.
30, sir, 30.
20? Okay. So yeah, that is also correct. So during the positive half cycle, we have the 20-volt V out. And then during the negative half cycle, we have a negative 20 V out. So basically, one of them will work as a Zener diode during the breakdown voltage, and then one of them will work as a forward bias. So and then vice versa. Okay. So if it's during positive half cycle, this is the that will work as a Zener diode during the reverse bias connection. And then once it passed through this one, so we now have a value of positive 20 since we deducted the rated voltage of this first Zener diode. But in here, we have positive to positive, negative to negative. So we'll just basically permit the flow of current. So still have positive 20. And then vice versa for the negative half cycle. So in here, it's forward bias. And in here, it's a reverse bias. So we have to deduct this 10 volts right here. All right. And then for your currents, of course, it's 20 milliamp and then negative 20 milliamp. Okay. So just let me know if, what is this? So just let me know if you guys have a question or if everything is already clear. So just give me a thumbs up. Okay, very good. All right, so let's now proceed to the next topic, which is the Zener diode as a voltage regulator. All right, so to begin with, let's take a look on the circuit first. So this is the basic composition of a voltage regulator using a Zener diode. All right. So if we have Bin right here, yes, we have RS, VZ, and then RL. So we have those fixed or constant components or values. I mean, not values, components. Okay. So if one of them is missing, then we cannot call this one as a voltage regulator. Okay. Anyway, so Zener diodes can be used to produce a stabilized voltage output with low ripple under varying load current conditions by passing a small current through the diode from a voltage source via a suitable current limiting resistor, series resistance or RS. The Zener diode will conduct sufficient current to maintain a voltage drop of the out. Okay, and then here are the definitions. Okay, or the legends of those variables. So V in or Vs are just the same. So that's our voltage input or voltage source. And then RS is our series resistance, and then IS is the series current. VZ is the Zener voltage, IZ is the Zener current, RL is the load resistor, and then IL is the load current, and then VO is the voltage output. Okay. All right. So here are the formulas that you guys need to be familiar with me. So supposedly you're going to memorize this one if we are only in a face-to-face method. Okay, but since we are in a online distance learning, so everything is open notes. So you don't need to memorize this one anymore, but maybe just familiarize this one so that you won't be having a hard time in recalling what is that formula again. Okay, like IL, and you already have an idea. This is where I can find the IL, and then this is how I do it, something like that. All right. Okay, so the first thing that you need to do is first check whether it's operating under breakdown voltage. Okay, because if not, then you don't need to proceed with this one anymore. Okay, so in here, if VTH is greater than VZ, so in other words, we must have enough uh, a voltage input or a voltage source to make this one a reverse bias connection, or to make this one a working breakdown voltage. Okay, because if it's not enough, then this won't work as a voltage regulator. All right, so this VTH right here is actually the Thevenin's voltage. So you guys are already done with the circuits one. So you guys already know how to transform this one into a Thevenin's voltage, okay, or the VTH formula. So just recall that one because we will not discuss that one in here since it's not part of the discussion. Okay. Or it's not part of the course itself. Anyway, so yeah, here's the formula. So Vs times RL divided by RL plus Rs. So of course you can use this one all throughout. So this one is heavily reliable since, again, just like what I mentioned a while ago, that we have a fixed components, and then their arrangement is also fixed. So you can use this one every time you're going to solve a Zener diode as a voltage regulator. Okay. So that's it for the first formula or of VTH. Or you can also use this one. So they are just the same. So Vs times RL divided by RL plus Rs. Okay, so those two are just the same. We also have here the IL current, or the formula for the IL, which is VL divided by RL, or IL is equal to VZ divided by RL. So you can use either of those two, so it will give you the same result. So in here, I think this one is very obvious. So in order to get the current of this load resistance, so of course you need the voltage load and then the load resistance, of course. Okay, but in here, this one is quite confusing since we are now using the VZ value, okay, the Zener voltage divided by the RL. So yeah, and as you guys can see, they are actually in a parallel connection. So that is why we can actually say that VZ is equal to VL, because whatever voltage that is crossing this VZ right here is just the same with this RL right here since they are in a parallel connection. So yeah, VL is equal to VZ. And then for the IS, we have the series current. So here's the formula. So it's Vs minus Vz divided by Rs, or you can use this one, Iz plus IL. So this Is right here will be divided into two. So one or some of the currents will go here, and then some of the currents will go here. So just add those two, and then you will get the value of Is. Okay, that is why we have this Is is equal to Iz plus IL right here. And then for the PZ, so it's very obvious. So we just use the formula P is equal to I times V, the power formula. So PZ is equal to IZ times VZ. Okay, so with that, you'll be able to get the power across your Zener voltage. So any clarification so far? All right, so it seems that there is no question. Anyway, so let us now begin with our example number 1 in Zener Diode as a voltage regulator. So find the V out, current across load resistance, current across series resistance, current across Zener Diode, and then the power dissipated across Zener Diode. Okay, so everything is the same. So whatever you guys are seeing right here, it's just that in here they now have values. Okay, so V1 is 20 volts, RS is 150 ohms. We have a Zener diode with a breakdown voltage of 8 volts, and then we have an RL of 1000 ohms, okay, or 1 kilo ohm. Okay, and then everything is the same. So we have the label of IS right here, and then the IZ, and then the IL. All right. So here is the solution. So actually, there is no tricky part in here. So whatever we have in here, we can just simply get that one, everything that we have in here, and then paste it right here, and then just substitute all of the given values. And then we'll be able to solve the VTH, we'll be able to solve the IL, the IS, IZ, or the PZ. Okay. So in here, I will leave the analysis part to you guys since everything is very straightforward. We just substituted all of the given values right here. And then just confirm that one. Okay, whether my computation or my final answer is correct or not. So in here, we have a VTH value of 17.39. So that is a greater than the Zener voltage or the rated voltage of our Zener diode. So we can now proceed in solving the remaining unknowns for IL, IS, and then IZ, and then PZ. All right, so were you guys able to follow the solution? Just wait a second. Okay, so just give me thumbs up once you were able to follow, or once you're done in analyzing this solution. Right, so no question so far. Like maybe this IS right here, the VA minus BB. So I put a label in here, which is a node A and then node B. So the voltage across this node A is of course 20 volts, okay, right here. And then what is now the value of our node B after passing through the series resistance? So in here, we have a value of 8 volts, or we can just actually simply get this one, since this one is higher than our Zener diode. So everything will flow in here, and then the voltage reading across this path is 8 volts. So that is why we have 8 right here. So 20 minus 8 divided by 150 milliamps is equal to 80 milliamps. So that is the current that is passing through this one. And yeah, so IL plus IZ should be equal to your IS. So 8 plus 72 is 80 milliamps. So those are things that maybe you can check, once you're done in doing this solution. All right, anyway, so let us now proceed to example number 2, wherein in here, there is now one missing variable. So in here, we have to find the minimum and maximum value of RL. So with those given values. So in a voltage regulator, so all of the components should be agreeing with each other, because if that one component doesn't match or fit with the other values of your components, then it won't work as a voltage regulator. Okay. So in here, we have an additional one, which is the IZM. So IZM is the maximum current that can flow through a Zener diode at its rated Zener voltage, or this VZ right here. So in here, we have an IZM value of 25 milliamps. Okay, so we have to find what could be, the minimum or the maximum value that we can put on our RL with those given values. So in here, it's kind of tricky, but yeah. So here's a pattern that I can give to you guys maybe, but it's not heavily reliable. But yeah, so all you need to do is find the mean first, the minimum value, okay, before the maximum value, okay. Or you can actually solve the maximum value first before the minimum value. So that completely depends too. So whatever is given, then you can start with that, okay, and then yeah, just go along with it, and then until you will be able to find the value of RL mean and then the value of RL max. So in here, this one is kind of tricky, since all you really need to do with this one is memorize the formulas for the RL mean, for the RL max, but for the IS and then IL mean, so they are still the same. Okay, so IS is came from this formula right here. Okay, and then IL is also the same. Okay, this one came from our general formula. Okay, anyway, so let's start with the RL mean. So RL mean is equal to RS times VZ divided by VS minus VZ. Okay, so this is the minimum resistance that we can put on this RL right here. So just substitute everything, since everything is already given, and then you will get a value of 50 ohms. Okay, so that is a minimum load resistance that we can put in here. And then for the RL max, we have to find the IS and then IL mean first. So this is another let's say pattern, okay, that you can do. So in finding the maximum value, so you have to find the IS and then the IL first. Okay, so for the IS, we have VA minus VB. So this one came from the from our general formula. So VA is 15, and then VB is 5. Okay, divided by RS, which is 100. 15 minus 5 divided by 100 is equal to 100 milliamps. So that is a value of our IS right here. And then for the IL mean, so we have this formula. So this one came from IS is equal to IL plus IZM. Okay, or this one right here. That one came from this formula. IS is equal to IZ plus IL. But since we're looking for the IL, so just transpose this IZ on the other side. So That is why we have this formula now. IL is equal to IS minus IZM. Okay, so just substitute everything, 100 milliamps minus 25 milliamps, and then we now have the result of 75 milliamps. Okay, and then in here we have the formula of RL. So this one actually came from, right, this is that one right here. It came from this IL is equal to VC divided by RL, or just the, the formula of the resistance, the ohms law itself. R is equal to V divided by I. Okay, voltage divided by the current. Oops. Number 3, number 2. Yeah, there you go. So we have here the value of BZ, which is 5 volts, and then the value of IL, which is 75 milliamps. And then just do the math, and then it will give us a value of 66.67 ohms. Okay, so meaning this is the minimum value that we can put on this RL right here, and this will still work as a perfect voltage regulator, and then we can have a maximum value of 66.67, and this will still work as a perfect voltage regulator. Or we can have values between 50 to 66.67, and then other than that, this voltage regulator might not work properly if it's not within the range of these values. So are we clear so far regarding with the formula of our RL min and RL max? All right, so if ever that you have a question, so just let me know. All right, so time check, we now only have 3 minutes left. Well, I think that's enough to have a short introduction with example number 3. So in example number 2, we have RL as a variable, or as a missing variable. In number 3, we now have VS as a missing variable. So it's the same. We have to find the minimum value, okay, or the maximum value of this VS right here. And then IZM is still the same. That's the maximum current that can flow on this Zener diode. And here is the formula, for the mean and then for the max. So everything is quite the same. So we have to find the IL and IS max first. And then here is a formula for the VS mean. So all you need to do is substitute all of the, unknowns, okay, in here, since everything is already given. And then you'll be able to get this answer. And for the IS max, so it's still the same. But in here, so there is a new one, which is this one. So we have to use this formula in order for us to be able to get the VS max. So what we did here is we transpose everything on the left side, and with that, we'll be able to get this one as our final equation. So 48.33 milliamps times 100 plus 7. Okay, and then just do the math, and then we'll be able to get 11.833 volts. So in here we have a range from 9.33 to 11.833.